Hello, everyone, and welcome to this session. My name is Davide Benvegnu, and I'm a DevOps architect in the Azure DevOps Customer Advisory Team, also known as CAT. You may have seen me around. I've been a speaker in some other conferences, especially here in Hong Kong. So if you know me, welcome back. If not, pleased to meet you. In today's session, we will explore how you can consolidate your infrastructure using Azure Kubernetes Service. And we will also talk about scalability and network security. So let's jump into the presentation. All right. As I said, we are going to explore how we can consolidate our infrastructure with AKS. You have some reference here for me. If you want to contact me afterwards, just feel free to use one of these means. Let's jump into the agenda. So we will have a small introduction about the application we will use. Is a Tailwind Traders application that you may have seen throughout the day already. We will dive into the AKS architecture, and we will talk about the differences between Kubernetes and AKS. We will talk about scalability, as I mentioned before, and network and security, especially focusing on pod identity and network policies. And at the end of the presentation, we will also see how to handle failures at both cluster and application level. So what is Tailwind Traders? As I mentioned, you've probably seen it before, but focusing more on the components of the application. It's quite a mixed application. We have some data sources like Postgres and SQL. It currently runs on virtual machines and container instances. So the application is partially already containerized. And it also uses blob storage to save some files and some components. So as you can see, it's quite heterogeneous, and we want to consolidate it into something more uniform. Also, we have some asks from our management about this application, and they go basically on resiliency, security, flexibility, and scale. So we want our application to be more resilient, to be more available, to be more secure, and to have flexibility in how we deploy, how we operate it, and we want to scale. If you've seen before, the application is basically an e-commerce application, so we want to be able to respond to peaks in demand, and also scale down when the site is not that much used. For those reasons, we decided to go with Kubernetes. But why? Well, first of all, because we want to have a uniform platform, and Kubernetes have some standardized API for infrastructure abstraction, which basically means that no matter what components you run in there, whether you run a database, whether you run your application, whether you run something else, you manage them in the same way because the infrastructure is completely abstracted from you. It has some self-healing capabilities that it's what we need for our application to be reliable. For example, if one of the nodes die, then Kubernetes will take care of that and spin up another one, or same thing for the parts of our application. Kubernetes enable a very good scalability. We can scale, and we will see this later, we can scale at node level, we can scale at individual component level, and we have also some automations in there helping us. And last but not least is extensible. We have, of course, a lot of plugins for Kubernetes that are developed directly from the Kubernetes code, from the upstream code, but there's a whole bunch of community developed extensions, including some that we will use today. All right, so we have our asks. We've decided we go with Kubernetes, but let's take a look a little bit deeper on what that means. First of all, let me point out that Kubernetes is a fairly complex platform. This is the usual Kubernetes architecture. And as you can see, I'm not going to go through all the components in here, but as you can see, it's fairly complex Because if you deploy upstream Kubernetes by yourself and you run it by yourself, then you need to take care of all of these components. You need to take care of the control plane, the one on the left. You need to take care of the master nodes and API servers, controllers, etc. You need to take care of its own database, which is etcd on the bottom left. And then, of course, you need to take care of all the worker roles, which means the nodes where your application is running at any level, and including security, including networking policy, and so on and so forth. So as I said, it's fairly complex. Luckily, Azure AKS comes in help because it's making running Kubernetes and managing Kubernetes much easier. In fact, you leave the management of the whole control plane to Azure, and you need to basically focus only on your nodes and your application. And it's a secure environment because your pods are scheduled on your nodes over a private tunnel. So there's no chance of other attackers trying to steal your traffic or connecting to your VMs or anything like that. So the only thing you need to do is work on your application, call the Kubernetes APIs that belong to the control plane that is managed by Azure directly, and start deploying to your AKS. So as you can see in this image, the abstraction is even greater. You don't need to take care of all the control plane and all the administration stuff on that part. And when it comes to networking, even as I just said, AKS abstract that from you. You still have full control on what happens on your worker nodes. This is a typical networking structure for AKS deployment, especially if it's, like in our case, exposed to the world. Remember that we are working on an e-commerce application. So you probably have some sort of ingress controller, and in front of that, you will have your security. So in this case, we have an application gateway to secure all the call from the external traffic. And then the ingress controller, through an external or an internal DNS, can connect to the worker nodes and directly to your containers running your applications. If you notice in the bottom middle, there is a small icon with a cat in there. That is the icon of Calico, which is one of the network plugins we will adopt later in the presentation to further secure our deployment and our pods. Last but not least, when we talk about AKS architecture, we have something in Azure called virtual node. This is supported also by upstream Kubernetes because we, as Microsoft, we deployed the extension to allow virtual nodes to be used, and we basically donated it back to the community, and they integrated that in the upstream Kubernetes. What the virtual node is basically in Azure the chance for you to not only have kind of physical nodes, basically VMs running your pods, but you can connect your Kubernetes cluster to Azure container instances that give you basically unlimited node or an unlimited capacity node with basically no infrastructure to manage. And it's actually much faster because even though with Kubernetes and with AKS and the virtual machine scale set, we can add a node at any point in time. That node will take few minutes to come up, maybe 2 or 3 minutes. But with Azure Container Instance, if you schedule a pod on ACI, that will start in seconds because all the infrastructure and all the components needed are already in the platform. So this will help us in our scalability issues. And worth mentioning that for availability, AKS now supports availability zones, which means that not only, as you can see here, you can run different instances of AKS across different regions, but inside the region, you can spread your VMs, your nodes, across different availability zones, which are basically different data centers. So even if one zone is down or has a problem,
or your node in that zone has a problem, you will ensure that the other nodes are still available because are in separated physical availability zones. So this gives you the maximum reliability possible because you spread across region and across regions. So that's a plus we have in here. How to set up this? Well, first of all, we need to create a VNet because we want our cluster to be in our networking resources. This is not strictly necessary, especially for test purposes. When you create a Kubernetes or a AKS cluster, if you don't specify this, it will create your VNet for you. But we want to have some more control over here. So all my examples actually are in Azure CLI. But of course, you can use the portal, and you can use also PowerShell if you want. But some of the features are still available only in the Azure CLI, and I'll point that out later. Again, so we create a VNet, and we want to create a subnet for our cluster to sit in. In our case, is the 10.2040. After that, we create another subnet because we want to enable virtual node, and for even more security, we want the virtual nodes to sit on a different subnet. If you've seen before, the subnet for our cluster for our normal nodes was 10.240, but now we create another subnet with 10.241 for our virtual node. Next step would be to create a service principal. A service principal is an object in Azure Active Directory, which allows you to give some roles or some permission to some objects. In this case, we create this as the command specify for RBAC, for role-based access control. We give it a name that can be whatever you want, but I advise you to use a meaningful name for the scope of that service principal. And we assign the role contributor. We need that because we want our AKS cluster to be able to add new nodes, for example. And for doing that, it needs to have some permission, some RBAC. And doing that, we allow our cluster to create other cloud resources. And we also allow the cluster to use some other resources as well. And we'll see that later. But specifically here, we want it to be able to create resources, including nodes. When this is done, we can proceed with the cluster creation. Now, this is the basic example in which you're just gonna pass your resource group, the name, and the number of nodes you want, and that's it. But this is, as I mentioned before, is a good example if you wanna create a test cluster, but it's not normally how you want to create your cluster in production. In fact, this is the way you probably want to create your cluster in production, in which you're gonna, as before, you're gonna say, I want this many nodes, but you also saying that you want it to be applying the service principal you just created, and you want to enable the network plugin. You want to do this right now because for network policy, network plugins, the fact you want to enable or not the virtual machine scale set and other stuff, those cannot be done after cluster creation. And this is very important. Kubernetes has two different plugins that can be used for networking, as the Azure, like in this case, which give you access to all the components in Azure, and for example, lets you add some new endpoints to the load balancer when you deploy a new application, or if you scale your application. And this, for example, it's not settable after cluster creation. You need to do it when you create a cluster. Same for the virtual machine scale set. Kubernetes and AKS can run on two different environments, normal VMs or virtual machine scale set. If you're not familiar with virtual machine scale set or VMSS,
It's a technology in Azure that allows you basically to clone and replicate VMs in a very dynamic and automated way. And it's perfect for Kubernetes because whenever you need to have a new node, if you enable the scalability, it will allow you to, again, add new nodes which are configured already like the master node, or I should say the template node, not to confuse. And so all the configuration and parameters will be there already. And again, this has to be enabled at cluster creation. And also these enable you to use the availability zones. And here you can specify in which zone you want your cluster to be. So in this case, we have 3 nodes here, and we are specifying the whole 3 zones, which means that by default, we will have 1 node in each zone. And last but not least, another thing that we need to do at cluster creation is to enable the network policy and to specify which network policy we are going to use. I'll talk about this more in detail later, but again, remember to do it at cluster creation. And since we use the availability zones, we also want to use the load balancer standard, which actually enable you to do this, because if you use the basic one, it's not zone aware, so you will not be able to use the availability zones. After cluster creation, what we are going to do is to enable the virtual nodes. By default, the virtual node is disabled. So whenever the cluster is ready, you can use this command to enable some add-ons. And in this case, we are going to enable the virtual node. And we are going to assign it to the subnet we created before to keep it separated from the other nodes. At the end, when everything is ready, we can use this other command to basically get the configuration and the keys for our kubectl, which is the command line that Kubernetes provides to interact with the cluster, to connect to our AKS cluster. You want to pass the --admin flag if you're using it as an admin, because you have unlimited access to your cluster, or you can, maybe avoid specifying that if you're using it just an operator. And again, as I said before, this will allows us to use, all the kubectl command that if you're using Kubernetes, you may be already familiar with. Again, I want to stress this out. Remember to kind of future-proof your cluster at creation by enabling especially CNI, the plugin for Azure networking, and availability zones, and at cluster creation, and also virtual node, because you can enable it now and maybe not use it until you're ready. But if you don't enable it now at cluster creation, you will not be able to enable it after. So keep this in mind. All right, so now we've seen how Kubernetes and AKS works. And we talk about how to create our cluster and how to enable our cluster with all the features we may need or we need. So let's talk about scalability. Let's suppose that our management asked us for a new service, and the service must, generate customer recommendations for previous orders. It must have its own deployable artifact and have documented API to interface with. So again, in this case, Kubernetes that we selected before, it's a very good option, because first of all, you're going to deploy containers into Kubernetes. So by basically definition, each container its own deployable artifact that comes in handy for this. You have documented API to interface with existing services. Especially, this is even more enforced by the Kubernetes API and the way how Kubernetes handles the different application and different containers in your cluster. And we talk about orders and everything, so most likely we need to be scalable for our application and especially for these services. So I think we made the right choice in using Kubernetes.
The way we want to implement that is, you see on the left, it's our Tailwind Traders application. And we decided to put a message queue service in the middle between the application and the new service, and to make it more scalable. So we are not going to be bottlenecked by resources. We're not going to be bottlenecked by any other thing. The application will somehow write into RabbitMQ, into the message queue service. And then our service, our new service, will take these messages and process whatever it has to process. So we have the scalability there at application level, but how we can ensure that the cluster is able to keep up with the requests. Kubernetes and AKS have two main scaling capabilities: the cluster autoscaling and the horizontal pod autoscaler, HPA. What's the difference between those? The difference is that the cluster autoscaler, as you can see here, will allow you to change the number of nodes. The way it works is that you have some, pods in here that are running your applications, and you somehow need to scale. You need to schedule more pods. For example, for what we said before, we want to, respond to higher traffic or to higher number of orders. But let's suppose that your cluster now doesn't have enough capacity in it. So maybe all your nodes are already full, and there's not enough resources. So your pods are scheduled in pending state, and it cannot start until some new resources are available. And this is where the cluster autoscaler here comes into the picture, because it informs Azure that there is additional nodes that are needed because we cannot schedule these pods in the existing nodes. So what Azure does, for responding to the cluster autoscaler, is to provision new nodes. And the number of those nodes depend on how you configure the application and how you configure the autoscaler. Can be one new node, can be two new nodes. You can customize that. And when Azure provision the new nodes, and then they assign it to the AKS cluster, then your pods can be scheduled on the new nodes. And this works also vice versa, because let's say you're scheduling these new pods for responding to higher order numbers, for example, and you have a peak. But then when the peak has passed, when there's no more request, you can actually instruct your autoscaler in deleting the new nodes, because maybe these pods are not doing anything. You want to save money, you want to save resources, and you tell the autoscaler to tell Azure to delete those nodes. So again, this works in both ways, if you need to add capacity and if you need to remove capacity. But let's say you have already enough capacity, and you just want to scale, or you want to change the number of your instances of your pods. Well, of course you can do it manually, but that would require you to monitor continuously your cluster and see if there are new incoming requests or new pods that need to be scheduled. This is not necessarily the optimal scenario. And this is where HPA, the horizontal pod autoscaler, is coming into the picture. Because what it does, it's continuously monitoring the server and its metrics and process it in here. And when there is a change in the metrics, depending on what the configuration is, it can add or remove number of instances or replicas from your deployments. So let's say, like in the case we said before, we have new orders coming in, or we need to process those orders. So most likely, we have already some pods scheduled, and those are not able to keep up with the additional work. So the horizontal pod autoscaler will notice that and will try to increase the number of replicas. So it actually will it will act on the deployment
changing the replica set and schedule more pods. So you will end up having, instead of 5 pods as before, maybe now you have 10 pods that are processing your orders. And again, this is fully customizable. You can set how many pods to increase, what's the maximum number of your pods, but also vice versa, what is the minimum number of your pods? Because as mentioned here, this works again also the other way around. So let's say you have now 10 pods and you don't have any more orders to process. You can instruct your autoscaler to remove 8 of those pods and leave 2 just in standby. And of course, these 2 things can work together, meaning that you can have the horizontal pod autoscaler trying to schedule more pods. And when it reaches the cluster capacity, the cluster autoscaler can add new nodes. But you can also do something different, which is using the virtual node. With horizontal pod autoscaler, you can actually instruct your routine to schedule the additional nodes on the virtual node. And as I mentioned before, this is super fast and it's probably the preferred way to respond to peaks because it's very agile, it's very fast. Just a small note here is that the virtual node is based off virtual kubelet, which is actually the extension I was mentioning before that we developed internally in Microsoft, and then we donated back to the community, and now it's part of the upstream Kubernetes code. And what it does is basically it registers itself as a node, like if it was one VM, but with basically unlimited capacity. So Kubernetes will see that as a normal node in which it can schedule as many pods as it wants. And another cool thing about the virtual node is that by default, by out of the box, it supports not only Linux containers, but it supports Windows containers as well. And of course, Windows containers now are also supported directly from Kubernetes, but it supports also GPU. One thing to remember here is that when you enable virtual node, by default, no pods are scheduled in that node. And this is because there's a flag in the virtual node to prevent that. So if you want to use the virtual node, you need to tell your cluster specifically or your deployment specifically to use that virtual node. And the way you do here is in the example that you see on screen. And basically, you need to add node selector with a toleration. So you need to use these lines and tell that those containers, those pods will be selected, will be deployed whenever this is matched in your cluster. So again, I don't want to go too much in depth in here, but the virtual node are created with these no schedule virtual kubelet IO that / provider toleration. And this part here just instruct your deployment to use that toleration as deployment target. So if you add this to your deployment, you'll be sure that your pods can be scheduled to the virtual node. All right, let's see this in action. So first of all, let me show you my cluster. You'll see here that I have 3 nodes, and each one is a different instance of the virtual machine scale set. And I also have a virtual node, which in this case is running on Linux. So I have 3 physical nodes and the virtual node. Now, if you want to see what's running on the cluster, you can see it here, and you will notice that there's only the RabbitMQ running in here. There's nothing else. But if we see our deployments, we'll see that we actually have a RabbitMQ consumer, which is our new service that is going to grab the data from the RabbitMQ service and process the orders or whatever we tell him to do. But there is no instance of the service currently running. And the reason for this is that we have implemented the horizontal pod autoscaler. And you can see here that we set 1 minimum, 30 maximum, but we set it to 0 replicas, which means that it starts at 0, it can go up to 30, and then if not needed anymore, it can go down to 1 again. Now, how can we make sure this works? Let me show you. So first of all, let me show you here. I'm going to use this script. This is a very simple YAML script, and I'm going to publish this service, which will just connect to our RabbitMQ using its own DNS name internal in the Kubernetes cluster, and basically just publish some message into the service. So as a result, we should see the RabbitMQ consumer, which is our new service, spinning up and start processing those orders. Let's see. So let me prepare something first. So we will have this here, which will keep polling on our pods and give us, the status. And same thing, I can put it here for our pod autoscaler. If you don't know, the -W, it stands for watch, which basically means that it is continually polling whatever commands you're giving to it, and whenever something changes, it will print out the difference. And finally, in here, let's apply to our Kubernetes the script that I just showed you. In some seconds, oops, sorry, that's my fault. All right. This again. There we go. In some seconds, we will see, you see it already. It's scheduling our containers on starting on our, virtual machine scale set. And now, since we don't have any more capacity, if you see here, it's scheduling on our virtual node. And if you look at the upper right, you'll see that there are some change in the pod autoscaler to reflect those changes. So yeah, this is how you can scale on, basically unlimited way, even though you may have only 3 nodes like I do, but then you can take advantage of the virtual node. Okay, so we've seen how to scale up and down with the virtual node. Let's move on network and security. Let me give you an introduction into the AKS security. In Azure, we have a whole ecosystem of security features around Kubernetes. We have, starting from the container registry where you can scan your image before deploying it, continuing with the Active Directory integration inside AKS, and all the RBAC controls. We have the app gateway. We have the Kubernetes admin secured. You can apply policy at the ingress controller. You can apply network policies. And not only, but you can also have encrypted communication from your AKS cluster to other services in Azure that are actually encrypted at rest. And finally, we also have Azure Key Vault to allow your application to consume secrets in a secure way. In this presentation, I'm not going to focus on all of those because that will be a talk by itself. But I'm focusing on the 2 most relevant here, which are the AAD pod identity and the network policies in here. What are pod identities? So
a pod identity is a construct that comes from Azure AD, and it uses the microservice identities to basically bind a specific identity to each pod. And this gives you total flexibility to grant access or remove access to and from Azure services directly to your pods. And this is an exclusive feature of AKS. It's not present in the upstream Kubernetes. And it is really powerful because it allows you to fine-tune your permission at pod level. To work, this requires two components: the NMI, Node Management Identity Server, which is a pod that runs in each node as a daemon set. And this basically listens for any pod request to Azure Service and ensure that the flow is respected. And then we have the Managed Identity Controller, MIC, which is a central pod which basically does the work. So the NMI just listen for pod request and try to instrument that. The MIC is the one that query the APIs for checking for Azure Identity Mapping for that particular pod. And this is more or less how it works in a slightly simplified way. So whenever the Kubernetes controller need some identity, it will talk with the Azure Identity Binding Service, and this will console the Azure Directory Port Identity through the NMI and MSI, and assign a token to your pod. And only with that token, then your pod will be able to, for example, here, connect to the SQL Server, to Azure SQL Server. And that, again, use the Azure Managed Service Identity. So as you can see here, nowhere in the flow there is a need for credentials, there's a need for secrets or anything like that. The other thing I'm going to talk about is network policy. Again, as I mentioned briefly before, there are two ways to implement network policies in AKS. And you can choose whichever you want, but you need to do when you created the cluster. Again, the policy option cannot be added or changed after the cluster is created. And this is why I was stressing that out before. As I was saying, there are two network policies, and they both only work when the CNI is enabled. As you remember before, I was saying that, again, there are two network plugins for Kubernetes. The one is the Kubernetes standard one, and the one is the Azure CNI, which is like more advanced. And network policies work only with Azure CNI. Talking about the different network policies, we have the Azure network policy and the Calico network policy. They are fairly similar. Both of them use IP tables in the backend. However, the Azure network policy basically allows the CNI to set up a bridge in the host, and all the communication actually goes through this bridge, and the bridge is the one applying the filtering rules. While the Calico network policy use again CNI, but then it basically implements the traffic filtering inside the local kernel. And so the policies are applied on the pod's network interface directly. Here you can see in a graphic way how this works. You can see this is the Azure network policy, and you have in here the packet switching and filtering that happen on the bridge. This is actually the bridge. And the policy manager just injects the IP tables rules into the bridge. While on the Calico network policy, which is slightly more secure, but of course, working directly on the Linux kernel, it has some overhead on the kernel itself. But if you work on some regulated environment or industry, this is probably the way you want to go, because this ensures the maximum level of security. And again, the Calico plugin actually acts at kernel level, and the IP tables rules are inside the kernel. So this basically allows the communication not to go out even before reaching the bridge level. Now, why are those policies important? Because for Kubernetes, the network topology is completely flat, which actually means that you're able to make any pod communicate with any other pod. Even though they are maybe in different nodes, and even though they are in different namespace, but as long as they are in the same cluster, any pod can talk to any other pod. And for security reasons, this is not maybe what you want to achieve. So network policies come in hand for that and allow you to control how pods can communicate one another. And let's see here in the demo how this could be achieved. So what I will do is show you that we don't have any network policy in this moment, and this will allow me to connect to a Tailwind Trader application pod from a completely new, totally unrelated pod. And then I will apply some network policy to stop that to happen. So first of all, let me run this command. This command will actually create a new pod in the cluster based on a completely different image. It's an Alpine image, and will let me run inside the pod. So now if you see, I'm inside that container, and I will try to connect, sorry, not this. And I will try to connect to this service, which is an internal host name for one of the pods we are running into our cluster. And you can see here, even though this is a completely new container that I've never run before, and it's in a different namespace and has nothing to do with the Tailwind Trader application, I'm able to connect to this service, and in this case, just downloading the file. Now, I really want to prevent that. So to do this, I will use this other YAML file, which is of a kind of a network policy. And what this does, this is the most, this is the simplest network policy you can create. And basically, it's saying that if an application is inside this namespace, then it can, this namespace with this role, then the pods can communicate one another. If the pods are outside of this namespace, they will not be able to communicate with those pods. So if we go back here and we apply this policy, again, there's not the right one. We apply this policy. Okay, we see that the policy has been created. And now, if I go back here and I try to connect with the same service, you'll see that it's not happening. Even if I increment the timeout, you'll see that this new pod, because it's in a different namespace, will not be able to connect to the service. And again, if you want to double check that, now I'm going to delete the network policy. Now the policy is being deleted. And if I go back here and I try again, you'll see that it's able to connect. I have an error message because the file already exists. So let me delete that. And here we go. So the network policy effectively helped me in preventing my pods to talk one another. And this is the way you do it. Again, that was the simplest one. You can have more selectors. You can have a more complex scenario there, but this is very effective to control your traffic flow. Okay. Last thing, how we can handle failures. Well, as I said before, AKS now supports availability zones, which allow you not only to spread your cluster across regions, but also to have different instances of your nodes inside the same region. And this again adds resiliency to single data center failures. Nodes, if you use VMSS, Virtual Machine Scale Set, the nodes are split across at least 3 data centers in the region. And again, this gives us fault domains to plan our deployment. So we can deploy to specific fault domains or to update domains. Be aware that the availability zone support for AKS, it's available, but it's still in public beta. So go and check on the link on the slide if there are any update about the release. But again, I would say start testing out with this feature because it's something you're gonna need for your production applications. But using availability zones, it's just a start. Of course, you need to be sure that you deploy with the number of replicas that matches the number of zone you're using. As you've seen before, in our case, we were using 3 availability zones. So we want to deploy with at least 3 replicas. So we are sure that each replica goes to 1 availability zone. And of course, you need to use an ingress controller that support availability zones as well. And this is why in the beginning, when I show you how to create the cluster, we actually use the standard load balancer instead of the basic one. And this is very important, the last point here. And it's something that a lot of people try to underestimate. But remember that your disks mounts inside pods, which means that if you're using the disk on a host machine on your node, you mount it into the pods. If the node is down, you will not be able to access that disk, which means that if you want to be more reliable, you need to plan using something like Azure Files or other external space, because you want to be able to, first of all, share the data across pods in case one node the pod died and need to restart. But also you want to be failure aware, and if your nodes die, you want to have your file and your information still available. So instead of using the node disks, it's very much preferable using something like Azure Files. And this is an example deployment for supporting failure or for handling failure. And as you can see here, we're going to use 3 replicas. So we make sure that the our application is spread across the different availability zones. And this brings us to the end of this session. What we've seen is that we've seen into the AKS architecture, and we've seen that Kubernetes is complex, but with AKS it's actually easier. The scalability is a first-class citizen that in your pod identity and Calico network policies are actually there to help, and you can consider using that. And you need to take care of your cluster. You need to manage your failures. So go and implement availability zones and proper settings in your deployments. And with this, I actually completed my presentation. Just a few things I want to point out. First of all, remember to enable network policies and other plugins at cluster creation, because you will not be able to do it afterwards. And go and play with AKS. If you haven't used it yet, I think we've shown it's a great tool, especially for scalability and deployments and your infrastructure consolidation. So again, I guess you want to go there and try it out for yourself. Thank you very much for joining me today in this session, and see you soon.